Hello, Augies Worldwide, and welcome to another Ask Dave video. Today's topic is one that was requested by several hams, and it has to do with the mysterious Malaysian Airlines MH370 flight disappearance. It was a large aircraft, I believe a Boeing aircraft, left from Malaysia on its way to China. And it was tracked as taking off for the Indian Ocean, and then it's disappeared. It's been aviation's greatest mystery, and since the disappearance of Amelia Earhart. Now, I want to talk a little bit about this and kind of some technical detail so you get some ideas that are going on. There was a 60 Minutes episode on Australian TV not too far back where some ham radio operator from Great Britain announced that he had used amateur radio techniques to locate where it must have gone down. The ham, it's clear from what he was talking about that it was Whisper, which is Weak Signal Propagation Reporter, and he was using logged data from the day of the disappearance, and he had constructed a flight path from the data. It's very controversial because there are those who say that you can't do that and those who say that you can. So I thought what I would do is just talk a little bit about it. Now, do I believe this guy or not? Well, I believe he did something. Whether he was tracking the flight is another story. And the inventor of Whisper has been on record as saying he doesn't think Whisper could be used for that. So I want to talk a little bit about that. Here are the points I want to make. First, let's talk about Whisper availability, even in the area. And then we'll talk about direct reception versus multipath reception. And then we'll talk about Doppler. Could Doppler be used for this? And some other investigations and Joe Taylor's thoughts on this, which happen to be hearsay because I don't have a direct quote from Joe, but I'll let you decide whether it's the right. I think it is. Now, let me tell you my bias right up front. I don't think that this could be done with Whisper. Whisper is not designed to track anything except the behavior of the ionosphere using its weak signal propagation reporter is what it is. It's propagation that it's reporting. Here is a picture of the airplane. This is Malaysia Airlines, and the flight number was MH370. Okay, this particular picture comes to us courtesy of Laurent Herrera, okay, and it's not quite public domain. It's under Creative Commons 2.0 attribution, so there I've attributed that. This is the same airplane taking off from Charles de Gaulle in Paris. Okay, so it's, like I said, a big airplane, modern airplane, equipped with modern avionics, and should have done very well. Now let's talk a little bit about Whisper. Joe Taylor created a program called WSJTX, and he's been updating it and updating and updating and updating it. Now there's a subset of that called Whisper. It's one of the modes that you can do. FT8 is another one of the modes that you can do, or JT65. There is a dedicated program for Whisper, but it does the same thing as this, so I just use this. I took this afternoon strictly recording. I didn't do any transmissions, strictly recording. And you can see that in a 2-minute period, this transmits every 2 minutes. That's important. The transmission is 2 minutes long, and then you receive for 18 minutes. Then you transmit for 2 minutes, and you receive for 18 minutes. And all of this is sent via internet to a website that I'll show you in a minute. This is what the waterfall looks like. This is in waterfall format. If you go into the Whisper program, it's in this format. with the waterfall going this way. Okay, so it's the equivalent display. And what you're seeing here is in a very narrow bandwidth. Okay, this happens to be on 30 meters, and it's going from 10 megahertz, 10.1400 megahertz to 10.1. Let's see, I'm looking at my radio, it's 138.7. So there is a 200 hertz bandwidth, so it's a very narrow band. And these are all the signals that are transmitting. You can see the various strengths of the signals. And then they are tabulated in another window, which I'm looking for. Tabulated in this window, okay? Now, this data right here is sent via internet to whispernet.org. It's WSPRNET.org. And let me just check that it's an ORG. Okay, sorry about that. A little delay there. It's whispernet.org. All of this information is sent there from the waterfall. We don't send the waterfall. We just send the decoded text. Let's take a look at what's in here. Okay, the 2208 is UTC, which happens to be today. It was about a half hour ago. The signal strength compared to an arbitrary reference inside of the program is either this top one is quite strong, it's 7 dB above, and then it can get extremely weak signals like this one, minus 24 dB below the threshold that it uses. So it can get some very, very weak signals. Look at DT. Here's the delta time from the sender's clock to the receiver's clock. Is, in this case, 0.1 seconds. The resolution on this is only 0.1 seconds. You can't do a lot of Doppler with that. You need a lot better time differentiation than that. The frequency is given to the megahertz. Note that the megahertz is the megahertz of the receiving station. Now I'm looking down at my little 7300. I have not checked it in the last several months for frequency accuracy. I think it's within a few hertz. Well, this is down to the hertz, but if it's only accurate to a few hertz, that means that the last couple digits of that are not necessarily worth anything. Now here's the drift during the period of time in hertz between the time the receiving station started to receive the station and the time it finished receiving it. The drift numbers are quite small, but can be large if you're using a radio that is not entirely frequency stable, so an older radio or something like that. Here's the call sign of the sending station and the grid square. That's the only location information you have is EN61 here, which is quite a large location if you're on the ground. Like I put down my grid is 6 digits as DM68CG, which narrows it down, but still doesn't narrow it down to where you wouldn't have to do kind of a search to find it. So EN61 is several square miles, okay, of possible receiving area. So that's going to throw off anything you're trying to do with the reception. The dBm is my recorded, this is the transmitted signal strength right here, okay? This is over here is the received signal strength compared to an arbitrary local reference. And this is the number of miles from the center of this grid square to the center of my grid square. Now, given each grid square covers several square miles at the 4-digit level, this could be off by a few miles, okay? So that gives you an idea. Here is my basic transmit frequency, and then these are the received frequencies in here. 10140206. This is the dial frequency, and its upper side band, so all the actual frequencies are going to be higher. This is up from that reference frequency here. Now I want to take a look at something. You can go online, as I mentioned, to whispernet.org, and you can click on the map and you get a map of the whole world. Now I want you to notice two things here. First of all, the density of hams on the U.S. East Coast. There are gobs and gobs and gobs. And this is only 30 meters. Okay, 30 meters. And this is the density on the East Coast. Look over here. Western Europe and the UK, and again, this is on 30 meters, is extremely dense. There are a lot of transmitters. Okay, a lot of transmitters. Now, if we look over in the area where the flight went down, the density suddenly disappears. I've actually zoomed in on this a little bit. Okay, the flight left from, I believe, Malaysia, okay, and took off this way. And this is the area that's been searched a lot in here. Now, see these French stations here? These are on an island called Reunion. And I don't know how to pronounce that in French. Some of the debris has drifted from the original crash site and landed on Reunion Island and a little bit on the north coast of Madagascar, which is right there. And this is Africa over here. So clearly the plane did crash, and it did break up. It was a terrible crash. No one could have survived it. All that's coming over here are bits and remnants from the original crash. Some aircraft components are made of a kind of a honeycomb, sort of foam type thing, so they can float. Pieces of them can float. The main airplane would have gone down. Now, let's look at what we've got. Remember that this is taken at the same time as this one right here. Here's your US, here's your European, here's Reunion, and then there are a few in the Perth area and a few on the east coast of Australia. There are a tiny number up here in the Philippines and India who participate in Whisper, and you've got some New Zealand. So in terms of having a number of stations transmitting, say for an aircraft right there, you don't have very much over here. So the data is going to be sparse. Now let's take a look at direct reception or multipath. All right, let's suppose we've got the airplane here. I'll just draw it as a little cross. There's an aircraft that's got a tail. Okay. And you've got a Whisper station here and a Whisper station receiving over here. Now you're going to get the direct path on the signal. Okay. You're also going to get an extremely weak multipath reception as it bounces off this and comes down here. You can measure the distance that it varies from this line by looking at the delta T as it comes off of here. Okay, now one of the problems that you run into with this, okay, is first of all, the Whisper transmission time, the Whisper packet, is 2 minutes, not seconds, 2 minutes long, okay? Meanwhile, the speed of light at, let's see, it's 186 thousand miles per second, or 300,000 meters per second. And if I've got that right, I may be off by about 3 orders of magnitude. Okay, this can go around the Earth 7 times, 7.5 times around the Earth in 1 second. Okay, that's the speed of light. So the multipath here could be measured with a fine instrument like a Doppler radar. The distance in time right here, I did something in the general class licenses when we were looking at multipath, showing that for packet, which transmits a complete packet in a very short period of time, how individual bits in there can disrupt each other if this is only a few miles off. Okay, so we're looking at multipath here. The thing is that the signal for, let me find the right one here. You've got 2 minutes from the time this starts transmitting here. Sorry, I don't have something that makes white. 2 minutes from there to there. Okay, 2 minutes. And so any multipath will be swamped in there, and the direct signal will be much stronger. Now, there is the possibility of this signal being the only one that's heard, that the direct signal is not heard, but a signal bounced off the airplane could be heard. Okay? And again, 2 minutes. It wouldn't be enough off from the 2 minutes to look like it would appear on this thing here. Again, they're 2 minutes from there to there. The multipath would be fractions of a second. And it wouldn't show up because, again, you're measuring only tenths of a second in terms of the delta time. You're not measuring down to the microsecond. You're measuring just tenths of a second, 10 to the minus 1 seconds, okay? And the received frequency here is measured by the receiver. Okay, so in terms of direct multipath, the problem is that this transmission is so long, and the way it is detected is by sending the signal here through an algorithm that pulls out a very few number of bits and pieces, and from that estimates these other things over here. Now, it's only 1 hertz off. I want to show you what happens with Doppler now. Okay, Doppler, you remember the old thing with the train. Okay, as it goes by a crossing, it's sending its frequencies here toward you, and you get the speed of sound plus the speed of the locomotive. And over here, the locomotive is receding from you, and so you take its speed, and you'll hear a difference in the frequency. Okay? And this is sound, of course, which travels about 650 miles per hour, or about 1,000 kilometers per hour. Okay, speed of sound. And you hear that type of thing go by. Well, that can be used by radar systems and is used by radar systems. Okay, the first radar that the British used was a Doppler radar. And I did some calculations, and let me see if I can find them here. Okay, 1.5 times 10 to the minus 6 times the frequency. So if the frequency is 10 megahertz, you would get 10 hertz, 15 hertz 15 hertz difference in frequency, okay? 15 hertz. Now that's definitely capturable here. It's 15 hertz, okay? Will it show up here if this is shifted? Now we got 200 hertz. If it's shifted by 15 hertz, would it appear as a separate signal? Yes. Yes, it may very well. Now, the problem is that you've got to compare the Doppler from several different stations. And given that we don't know see, we've got this dt over here. This is the time, okay, but we're talking hertz. Now, suppose that this hertz changed by 15 plus 15 hertz. How would you tell? What are you comparing it against? You've got to have some form of comparison. That's the thing about Doppler radar. Doppler radar gives you the speed. Now, if you've got this aircraft going this way, and your Doppler receiver is right here, it's looking this way, it'll get that full speed. But if it's looking this way, it only sees a component of it, that component right there. Okay, you need multiple radars reflecting off of something, or very precise electronics, such as is found in modern radars, to calculate the position when the data that you have is speed. Okay, if you have a couple different places, like the British used to do in their chain home, you'd have multiple stations listening, and they would get different frequency delays, and they were able to get a pretty good idea of the position of the aircraft that was flying over the channel. Note that the transmitters were quite high power, okay, and the receivers, which I believe are on separate towers, were the best money could afford at the time, which was an HRO or something like that. And they used phase differentiation to track the radios. They used a little device called a goniometer, but anyway. Now, how do I know about this sort of thing? Well, I was in radar in the Air Force way back when, learned how different kinds of radars worked. I also have a master's degree in engineering, which deals with communications, for example, satellite signals and stuff like that. And I spent a fair amount of time studying modulation theory, and even into the radar equation and so on. So, yeah, I've got some history on this, and I'm telling you that what they've got here, you know, until this ham from Britain reveals his material in a technical paper that can be peer-reviewed, we don't know. Now, if you want, let's see if we've covered all the topics that we wanted to cover. Doppler. Okay, we've talked about the fact that whisper is not a big thing in that part of the world. We talked about direct reception and the possibility of multipath, which will give you intersymbol interference, but whisper is designed specifically to avoid intersymbol interference. Okay, that's why it sends the same thing over many times, and there are codes that you can use, ways of bit fiddling, to avoid the problem of intersymbol interference in a received signal, because it is a problem in radio communications. We've talked about Doppler, how the traveling of the aircraft probably at about 500 miles an hour, Mach 0.8-ish, would give you some Doppler, but what do you compare it with? Maybe this ham has found something to compare it with. I don't know. Now, I just wanted to talk about some other investigations. There's a whole hobby built up around this. This is, and I'm going to just hold this here, this is a 2-line URL. https://mh370.radiantphysics.com/2021-1219. Whisper can't, no hyphen, can't find MH370, ended with a backslash, or a forward slash, will take you directly to the article that talks about this. It's by Victor Iannello, okay? And he contacted Joe Taylor, and this is what Joe Taylor had to say. Now, this is Victor speaking, so this is technically hearsay. I understand that, but I can't find a direct article by Joe Taylor. But he says, I asked Joe Taylor for a comment on the material covered in this article. Here was his response, shared with his permission. Now, this is Joe Taylor speaking. As I've written several times before, it's crazy to think that historical whisper data could be used to track the course of ill-fated flight MH370, or for that matter, any other aircraft flight. And then this little zinger here, I guess he's tired of getting this question. I don't choose to waste my time arguing with pseudoscientists who don't understand what they're doing. Well, am I a pseudoscientist? I suppose I might be. I'm a ham. But I'm also a degreed engineer. So my bottom line on this is, until someone like Joe Taylor has passed judgment on a technical paper written by this British ham and has looked at the equations and the data, and someone else has been able to duplicate the results, until that happens, I don't believe it, okay? And I don't think you should either. Great conspiracy theory, but no, I don't think so. So there you have it. If you would like to help this channel flourish, you can put a little money in the pot by going to dcasler.com/support. If you would like to submit a question, the best place to submit a question that you'd like me to answer would be to send it to my column in QST, which is to Ask Dave, all one word, at arrl.org, not net, .org, okay? And I'm choosing from those to make these, and I will also choose from them to put things into the monthly column in QST that goes by the same name, Ask Dave. So until we next meet, 73.